we just need to apply this. So 6.4, we're talking about related rates. Again, we had a worksheet on this, and the worksheet outlined these same steps, or it should have been the same steps as I'll do now. So step 1, we're going to read our problem carefully and label the givens and unknowns. And step 2, we're going to draw a diagram. These two can kind of happen concurrently. They don't need to be two distinct steps. You can switch back and forth between them. Step 3, we're going to write an equation relating the variables in the problem. Step 4, we're going to use implicit differentiation. And we're going to do this with respect to this WRT, as always, is with respect to time t. What I mean by that more explicitly is that I'm going to now have dx dt's and dy dt's because of the context of the problem. So again, because we're in a real world problem, our x is moving as a function of time, our y is moving as a function of time. Again, we talked about how you can get very deep and existential about how everything is bounded by time, but the most important part for us today is that when I take the derivative of an x term, I add a dx dt. When I take the derivative of a y term, I get a dy dt. Now, steps 5 and 6 are interchangeable. I'll write them as I had them on the worksheet, but know that you can change these things around. So we're going to solve for, I'll just say the thing we want. By thing, again, I mean most specifically the derivative that we want. Okay, there is a rate of change that the problem has asked us to find, solve for that one. Step 6 is going to be plug in given values. Okay, again, these two are interchangeable. We saw that many of the times I just plugged in things first and then solved for the only thing remaining. I found that to be an easier method. All right, so let's do an example of a ladder problem. You guys have seen now a number of problems on these. You know that I love a good ladder problem. I think that they're concise and nice, but let me pull up a couple problems. All right. So I'm going to do an example. I don't think that these matter too much. So yeah, I'll do number 2 on the worksheet, on the exam review worksheet, so you guys can follow along. So we have a 15-foot ladder against the wall. Let me double check my solutions for this guy. Yeah, so we have a 15-foot ladder against the wall. And it's being pushed towards the wall at a rate of 0.25 feet per second. and we're going to, let's see, where is it? We're asked how fast is the ladder moving up the wall at 12. At 12 seconds. Okay, so a couple of things. Don't let this problem intimidate you. I know that it seems scary because we're not actually given a distance. It's not too bad, okay? So we'll use the rate of change given, as I say in the hint, we'll use the rate of change given to find the specific measurement at that time at 12 seconds. But let's draw a diagram first before we get too far ahead of ourselves. So I have a building, I have the ground, maybe you include a couple of windows on your building, I don't know, maybe a little door, maybe some people in there, and then I have a ladder leaning up against the building. This is the ground, we've got like a little flower or something there. Okay, so this is the ground, this is my building. My ladder is 15 feet long. I'm going to call this axis on the ground, I'm going to call this X. We'll call the one on the wall Y. Again, I like X and Y. X is almost always my horizontal axis. Y is almost always my vertical axis. You can change them. It doesn't really make a difference. And 15 is going to be Z. So I'm going to set up kind of a chart of my values here. So I've got X equals, Y equals, Z equals. And I'm going to want to find something out about dx, dt, dy dt, and dz dt. Okay, so let's fill in what we can right now. So, do we know what x is? Not yet, but that's a quick calculation. We'll see that in a second. I should also include our ladder starts at 10 feet. From building. Okay, that's written in the problem if you look at number 2 in the 6.4 section of your review worksheet. Okay, so it's tempting to want to put 10 in for x, but that's not quite it. We want to know how fast the ladder is moving up the wall after 12 seconds. Okay, so we're going to skip x, we're going to skip y. We know that z is equal to 15. We know that dz dt is 0. Ladders shouldn't be growing or shrinking. We don't have that fancy of a ladder. Okay. Dy dt, that's what we want to find, right? How fast is the ladder moving up the wall? This is the one that I want. It's not just something I don't know yet. And then dx dt is 0.25 feet per second, and this is where in class I'd say is it positive or negative. Now, because I'm pushing the ladder towards the wall, it's moving in the negative x direction. In all of these problems up to this point, we've seen that our ladder is sliding away from the wall and sliding down, okay, doing something like this. But in this case, we're pushing our ladder towards the wall, so it's going up like that. So our y should be growing, this value should be positive, but this value is certainly negative. All right, now let's find what x and y are. So to find x, what I'm going to do is use the rate of change. I know that I start off at 10 feet plus however much we moved in 12 seconds. Okay, so I started off at 10 feet and then I have however much I moved in 12 seconds. This is 10 feet plus negative 0.25 feet per second times 12 seconds. Okay, so this is going to give me 10 plus negative 3, which gives me 7. I realize now I'm writing way too big for the space that I have. Okay, so this guy is 7. To try to reserve some of that space, I'm now going to use the Pythagorean theorem that relates all three of these things, x squared plus y squared equals z squared. So I see that for x I have 49 plus y squared equals 225. So here y is going to equal about 14.697. Okay. Again, you can see my notes on this. So I've got 14.697. All right, now the thing I want to do is establish my equation x squared plus y squared equals z squared. I want to implicitly differentiate this, so I get 2x dx dt plus 2y dy dt equals 2z dz dt. Again, this is what I mean because all of these things are happening in relation to one another over time. All of these x, y, and z points are subject to time. Don't plug in values until this step. But now that we're here, I can plug some things in. So I get 2 times 7 times negative 0.25 plus 2 times 14.697 dy dt equals 0. Again, I plug in this 0 up here, and that last term zeroes out. Solving this guy, I see that I get dy dt equals 0.1191 feet per second, which is positive. That's exactly what we wanted. Our ladder should be moving up the wall because of this motion. Okay. So again, as I say on the exam review solutions, this is definitely a few steps harder than something that you would see on the exam. Okay. I do love ladder problems, don't love this kind of like intermediate stuff. And also if you look at finals and things like that, you'll see a problem like number 1, where you see that we have things like a sphere. For anything that's like a sphere, I think I'll write this on this. For anything that's like a sphere or a cone or a cylinder, if I asked you something about those, I would give you the equations. Okay. So what I really care about you knowing the equations for, I want you to know the Pythagorean theorem. I want you to know things like the area, perimeter, and volume of rectangles / boxes for volume. Okay, so again, spheres, cones, cylinders, weird shapes, things like that. I'll give you the equation, but it is worth trying out those examples, and also try out an example with similar triangles, because that can come up too. I do love a good similar triangle problem. We talked about that a few times after class or during office hours. Okay, so go and look through and see how those are done. All right, moving on, we're going to talk about section 9.1. Section 9.1, we talked about graphing in 3D.